Hello and welcome to our webinar, An Introduction to Fracture Testing. Thank you so much for joining us today. I'm Harriet Barnes, your host for this session. For this discussion, Peter Bailey, one of our senior application specialists, will focus on the basics of fracture testing techniques and how our new Bluehill Fracture software makes the crack propagation and fracture toughness testing process easier for operators. For today's presentation, Peter will use about 40 minutes for his discussion, and then we should have some time for questions, where we also have Lisa Goodwin, Market Manager, helping out to answer these. So I encourage you to send in any relevant questions you might have as we go along. So with that said, I'm going to hand you over to Peter.
Thank you, Harriet. Good day, everyone. Recognizing that some of you may be ahead or behind our time zone, we're currently based in the UK, so it's mid-afternoon here. So, as Harriet says, and on the advertising for this webinar, we said it was an introduction to fracture testing. I'm going to talk about some of the concepts for a while, and then a little bit about the practicalities of doing tests. And then a little bit about our most recent products, in particular software around fracture mechanics analysis and test running. So I am, just to give you a slightly more of an overview, starting with a little bit of history about fracture toughness in metals and how we describe it. We'll sort of step to one side to talk about fatigue crack growth, and then talk about the practicalities, and finally on to the bit about Instron products and what we can do to help you along when you come to do those tests. So, starting from the very beginning, fracture toughness. What are we going to describe it or define it as? It's how we describe a way of describing the resistance to a local failure near a defect. Now, usually that is a crack, but when you look at larger pieces of metal, then it could be a small inclusion of some non-metal particle, or it could be a void, for example, in a powder metallurgy product. Two more points. So why is it relevant in materials physics? Well, when you do, as we'll come on to the original origins of this, when you look at the molecular model and you say, well, what should the strength of my material be? It's a lot, and I do mean several orders of magnitude higher than when you do a physical measurement. And this is really what started out the idea of defects and cracks and crack growth. And closer to perhaps my own heart and to what we as a materials testing community do is, why is it useful in engineering? And really there, it's about critical structures. And when you build a large structure, a safety critical one, like an aircraft or a pressure vessel, you need these things. They develop defects, or they're built with defects that you never knew about. And in service, you need to manage the safety and know that it will stay safe throughout its life. So that's where this data goes. That's why we want to know about fracture toughness. Skipping on to history, then there's a huge amount of history, and there are an awful lot of people who've thought very hard about this over the last century. But four names that you will definitely hear of in this field. You start with Griffith, and Griffith it was who started work just before 1920, and he was the one who came up with the idea of, well, what's the theoretical strength of a piece of glass, and then built from there into, well, why isn't it that strong? Now his approaches were very, very pure and theoretical, and a little while later, George Irwin came along and started to build on that and try and make it a bit more practical and try and direct it towards engineering materials, well, realistically metals at that point. And he sort of developed the concept of stress intensity, which we'll come back to in a minute. You'll also come across Rice, James Rice, and now he is still alive. I think he's about 79, and he really brought around some of the ideas to do with very high strength, more high toughness materials. Last of all, perhaps the most likely one that you'll have come across if you work in fatigue and fatigue, then is Paul Paris, and he was very much the father of fatigue crack growth studies. And please excuse my typo on that slide. Moving swiftly on. So there are many other people, and there's been a lot more development of theory over the last 30 years, but those are perhaps people with seminal concept who developed seminal concepts. So what about the history? What's the background of fracture toughness and its application? Well, actually, let me give you 3 examples of where it wasn't applied. First off, the Boston molasses flood, which certainly in Europe is something very few people have heard of. And this was an early industrial accident. Well, an early 20th century industrial accident. A very, very large storage tank, literally millions of gallons of molasses. And you can see in the illustration here, this is a very large area destroyed by this huge volume of liquid. And temperature changes in the contents of this vessel caused a pressure buildup, and it caused it to rupture due to poor material or damage or crack development at the joints. Certainly that's the assessment. Getting a bit more serious, just post-Second World War, some people may have heard of the Liberty ships. They were a fantastic new design, all welded construction. So doing away with the slower and heavier, more labor-intensive approach of riveting everything. What this means is that your metal hull of the boat is effectively one single piece of metal. Well, close enough as far as fracture mechanics is concerned. And there were square hatches, and as they went about the ocean, there was cracks developed, and then, as you can see in the right-hand picture here, the entire hull split in two. And there are pictures out there, if you go and search for them, of a number of these vessels, and they're literally split into somewhere near the center of the boat. So really quite serious. And my third and final example, the most likely one that you'll hear for people to have heard of, and also the most serious problems, the de Havilland Comet, the world's first jet airliner. And a lot of people think that it's, really quite it shaped the way that jet airliners have been ever since. And they really did attempt for nice, elegant lines. But so they started, and then within a couple of years, there were a series of catastrophic accidents. Now, 2 of these hull failures were in flight, which is quite horrendous, obviously. And there were several more during takeoff and landing. And what you can see here is that failure investigation on that, again, that right-hand picture, you see the cracks starting from the corners of these square or rectangular windows. So there's a theme starting here about corners in structures. So that brings us on to kind of the seeds of how fracture mechanics works as a basic idea level. We're going to talk about stress concentrations. So if I have a nice plain sheet of material and I clamp it nicely at both ends and apply a force, I'm going to get a uniform stress field. Nice, and you've got the flow lines there in this illustration. Now, if I cut into it, I've got the same amount of force, and it's nicely spread at each end, but we've got to force it through this tighter section where there's a notch, and hence it gets termed a stress raiser, because the bit near the pointy end of that notch is carrying a much higher stress than the rest of the wick. And this is going, so hence we start describing this as a stress concentration. And you can visualize this using transparent polymers. People have done experiments for many, many years. You can use optical techniques to show you how the stress intensity builds up. And you look at the colored fringes on this, apologies for the image quality here, on the right-hand side, and you see the denser the series of fringes, the tighter the concentration. And that's that corner there, where you've got this very, very tight concentration of stress. So this is why materials fail or start to fail where there's a corner, as it were. Equally, it doesn't have to be a sharp corner. Even a hole or some other feature in an engineered structure can act as a stress raiser. So this is sort of the idea, the background, and why it matters. But different materials do behave a bit differently, so we need to characterize that failure in different ways. And while it's a great simplification, all the theory around this splits into two groups. One is what we term brittle, sometimes called brittle, or it's linear elastic fracture, and that would probably correspond to a lot of the high strength aluminiums. And you can see in my photograph on the right hand side, that would be the top specimen there. And you can see fairly smooth surface, fairly clean break, and when you're loading a structure like that, it's all fine, and it's all nice and reversible. Everything's elastic, and and up to a certain point, you can unload it, and everything will be, relatively speaking, fine. But once you get to that critical point, that critical amount of stress at that corner, at that notch, the failure is rapid and it's catastrophic. That crack is going to start running, and it will run. In a specimen, it might be centimeters. In a large structure, it could be many meters. On the other hand, as we start to move into tougher, higher strength materials, so steels in particular, then you start to see not purely elastic behavior. So what happens here is that there's plastic deformation happens near that defect, near that crack, that notch. And then you get more gradual tearing. So it's not quite such a rapid and catastrophic failure, or not necessarily. Certainly you see in the bottom specimen on the right hand side, you can see the sides of the specimen are pulled in. There's a lot of ductility, a lot of plastic deformation happening right the way through. Now that bottom one there is ductile austenitic stainless steel, if you care about that sort of thing, and you can see a much rougher surface, and that tears very gradually, but it's going to hold that force for much longer as it tears. And you do get somewhere in between some of the more brittle steels. The central specimen that's an EN24. So it's a high strength steel, but it's a lot more brittle than stainless. you've still got that really rough surface at the micro or meso scale, but it's got a clearer point at which it starts to rip. So there is, as I say, a spectrum, but we do broadly group into brittle materials like aluminiums and often titanium alloys, and more ductile materials like steels, most typically. So if we're going to actually use this in a more scientific fashion, we need some parameters. We need real measurements, shall we say, that we can use, both for measurement and to design our structures with. So there are three key ones which I want to highlight to you. There's stress intensity, which we've already talked about. There's J integral, and there's CTOD, that's crack tip opening displacement. So what are these? What's he talking about? Right, once again, similar diagram to what I said. We're looking at stress intensity is the localized stress. And you see the units here are megapascal root meters, and that's describing how tightly the stress is concentrated at the crack tip. J integral is about, it's a mathematical description of the energy in the material. And it's describing the work done in making that crack longer. And sorry, I should mention the units again. You've got kilojoules for energy and per meter squared, so that's the increase in the area of the crack. And last of all, CTOD, you're measuring displacement physically at the tip there. Along with that, it's not particularly popular at the moment, but in research terms, there's also crack tip opening angle, which is effectively describing the same thing, but it's never made it across into mainstream use for engineering. Not yet, at least. So what are these three? How do we choose which one? Well, stress intensity, okay, it's a relatively easy measurement, and it's relatively easy to apply for design engineers. And it works really well if you've got a fairly brittle material. However, we don't only design with aluminium and titanium. So J integral it's a lot more complex to determine experimentally. But in principle, you can apply it to absolutely anything. If you really want to, you can apply it to a brittle material as well. Finally, CTOD, again, it has its origins quite early in toughness, in the history of toughness testing, and you can make a basic measurement very easily, but you can also analyze it in a more complicated way and tie it in with the J integral, with the energy. So 3 different parameters that we can choose to use. But coming back to our idea of toughness, we need to work out how to describe it. And really, we're interested, when is the point of no return? When's the critical point? So the aim is to describe the point at which there's an instability. But how do we do that? So for some materials, on the left-hand side here, I've got a little graphic loading up a brittle material, and it's all fairly nice and linear, nice and elastic, until only just before it snaps suddenly and then fails really quickly. On the right-hand side, though, we've got a much more gradual roll off, and it sort of starts to slope over, and then it curves over, and then it sort of rolls right down and tears, and then all is lost. But where's the critical point there? Is it the peak? Is it where it stops linearity? Is it past the peak where it's definitely tearing? There are different approaches that need to be taken. So visual determination, and that is actually used for some tests in composites and polymers still, but it can be difficult and it can be unreliable. Certainly, it's difficult to make it repeatable. So what we do is we use an algorithm to determine a point from some continuous measurement data, because for these metal specimens, we've had test equipment with good transducers for many, many decades now. So we're used to having continuous measurement data. So let's look at a couple of the key ones here. Taking the simpler case first about stress intensity, the parameter that you'll see mentioned is K1C. Now we're talking about K, the stress intensity, mode 1, which is opening the crack straight out, and C referring to critical. And what we're going to do is we're going to find a single point at which the force displacement becomes nonlinear. So the point at which it's not acting like a perfect spring anymore. And you look at some test data like this, you fit the straight line portion of the curve, and then you look for a certain offset from that, which is it's basically a way of repeatably deciding when your data is no longer linear, when it started to break. Going on to the more complicated case, where we've got some ductility. So in this case, the crack tip doesn't just sort of stretch reversibly, it first deforms, it stretches plastically. And if you unloaded it, it would stay stretched a bit further open. But it's first deforming and then sort of just getting wider. Then it starts to tear. So now we need to understand how that energy we're putting into it extends the crack. And we build what's called a resistance curve to do that out of a number of points. And the critical point we decide is where there's a measurable amount of stable tearing. And that's measurable in the sense of if you were to try and physically measure it, and we build that from the data and determine it. So I've labeled my diagram here. It's pretty much at where the point of the arrow is, where our two curves intersect. And that's equivalent to 0.2 millimeters in most test standards, 0.2 millimeters of crack extension. So that's the width of a human hair, which is probably, it's a rather optimistic limit for what you could visually resolve if you were trying to do it that way. So I've hurried through that. Perhaps how are we doing for time? I've talked quite a lot about the general idea. I'm not going to get into the sort of the minutiae of the equations and exactly how the calculations work. There are far more learned and far more effective people than me to talk to you about that. The calculations are all laid out very clearly in the standards and in textbooks over many years. I'm going to take a little diversion now and talk about fatigue crack growth, because before you get to this catastrophic failure point, then cracks usually grow quite slowly in service. And if you work in fatigue, then general fatigue tests, actually what's happening, they may not be visible, but your fatigue loading on a specimen creates lots and lots of micro cracks within a specimen as the test progresses. And eventually failure happens when one of them grows or several of them join together. But for sometimes we need to understand a bit better than that. We need to understand what happens when you've got one major crack and how can you use that in a structure. So why do we care about this? I'm going to bring it back to the idea of, in this case, aerospace structures and the way that you operate them. So you have periodic inspections for damage or for cracks. And when you do that, there is a minimum size of defect. So let's say realistically, you've got hundreds of square meters of aeroplane to inspect, realistically, you're not going to be able to inspect well enough to see anything that's, let's say, smaller than 5 millimeters. I don't know what it is in their standards, but let's say it's something easy to observe with the naked eye. So you're going to do that every, let's say, 1,000 hours of flying. So what you need to work out is be sure that your crack, if you get one, it mustn't grow from not recorded to dangerous in that 1,000 hours between inspections. And to do that, you really need to understand how the crack grows under fatigue rather than under catastrophic loading. And so you can see how this is really, really especially critical for the aerospace industry. But there are other structures where it's equally important. So things like nuclear pressure vessels are similarly really obviously critical. So again, we need ways of describing this behavior. There are similarities with basic fatigue, but we're no longer interested in cycles to failure. We're interested in how the crack grows with applied loading cycles. And instead of the general stress that's applied, we're interested in the stress intensity. So we're only interested in what's happening at the crack tip to drive it forward. So we come back to using the stress intensity because we're staying nice and elastic conditions. So when you start looking at that and plotting comparisons, instead of an SN curve, you come up with something that looks a bit like this, and is generally referred to as a Paris curve. And you divide it into 3 regions, and region 1 being where the growth is vanishingly slow, and you're unlikely to actually drive crack growth. Region 2 is your nice predictable region where you can say, well, at this fatigue loading in terms of stress intensity, you're going to get this rate of growth. And it's nice and predictable. Region 3, we stay well away from, because that's getting into the territory where you could come into catastrophic failure. And then you're interested in fracture toughness instead. So one other thing that's important with crack growth is we need it in order to create a truly sharp crack. Because when we want to measure the toughness, we don't actually know if we have a blunt crack. We're not quite sure what we're measuring. And we use fatigue to create that sharp crack because a machined notch is never clean enough, sharp enough. And that's partly because if you use traditional machining, it puts plastic strain into the surface. I borrowed someone else's diagram here about machining and what happens during that as you put a machine tool across the surface of a piece of metal. But it also, you talk about EDM or spark wire erosion type methods. They have their own problems, and they can cause almost the opposite issue of hydrogen diffusion into the surface. In both cases, you can change your measurement. And we don't want that. We want a repeatable measurement. So residual stresses change what you're actually doing to the specimen, and chemistry or microstructure changes will change the toughness in reality. So the last thing you want to do is affect your measurement by your specimen preparation. Hence, you grow a fatigue crack to get past that and have a sharp tip. Measuring toughness, I'm looking at the time and thinking I'm probably talking too much, so I'm going to skip a little bit. Measuring toughness, people have been doing experiments heavily since the 1950s, unsurprisingly, and really developing repeatable methods was very popular from the 1960s. The earliest standards were international standards, although in this case, a British standard came out in late 70s. And we've seen sort of test methods emerging in forms which look familiar from about 1990. And there's been some really great improvement on reproducibility since then, but the concepts were getting to a point of being fully mature about them. Today, if you look at most common test specimens, you come down to two basic formats. Other ones were investigated and didn't really survive the evolutionary process. There are some other shapes used for particular material forms and special cases like pipes and that sort of thing. But fundamentally, you'll see something with a square side view, a CT specimen, or a rectangular side view, the bend specimen, an SENB specimen, and you load these either with tension or with bending, and that brings me on to my next slide of the test setup. So in both of these cases, you're using rollers or pins, and they're allowing the specimen to rotate. So as you grow a crack out from that notch, which you can see, hopefully you can see it clearer on this photograph. Obviously, the specimen actually does, the two halves of the specimen rotate away from one another. And so you need to let that happen with the fixturing. You also need to measure what's happening locally with the specimen, rather than purely trust how the entire crosshead or actuator are moving apart. So you use what we tend to call a COD gauge, which is a crack opening displacement. It's effectively an extensometer with a very specific purpose, and it measures the mechanical deformation at the front of what we call the front of the specimen. Now, all this sounds relatively simple, but it does come with the health warning that you need that crack to grow nice and straight across the specimen. And if you don't have your machine aligned well, then it won't. There are some, for those who work in materials testing a lot already, then you'll be aware there are some fairly conventional approaches to measuring machine alignment. But when you do crack growth, it's actually far more sensitive than those. And I've just put up two little photographs to illustrate what happens. And on the left-hand side is a lovely straight fatigue crack, followed by a rough surface where it was torn apart in a J1C test. On the right-hand side, you've got the same thing, but with a distinctly wonky, shall we say, a distinctly asymmetric crack front. And this really does break the rules for getting a good measurement. And that's to do with just a tiny bit of misalignment, meaning that there's slightly higher stress or stress intensity on one side of the specimen than the other, so the crack has grown faster on that side. Words about pre-cracking and how you control that. So superficially, it's like a high cycle fatigue test. You're applying a force-controlled sine wave. But you do a bit more than that, at least in modern times, most people would prefer to. You monitor the stiffness of the specimen, and from that, you can calculate the crack length. And based on that, in turn, you can adjust the forces to give you the right stress intensity. Now, why are we worrying about this? What it does is it allows us to keep the stress intensity nice and low, and so that it's not going to do unpleasant things to the material ahead of the crack tip. And it also means that we can actually just monitor it without relying on visual measurement, so that we grow our crack through that volume of material which I was talking about, where we don't know what it is, but also not so far that we get close to the back of the specimen and all our calculations aren't quite right. Once we've pre-cracked our specimen, then we get on to doing a main test. So our test control is actually not horrendous in complexity. For a basic test, something where you're just going to do a single pull until it goes snap, this is typically a K1C measurement, it's a simple ramp. We've got no crack extension to monitor because we know that nothing will happen until our critical point, and we've really not got very severe and any significant time dependence. When we start looking at more ductile tests, for example, a J1C test, what we do is a ramp, but periodically we hold for an amount of time and unload a little bit and then carry on. And what this allows us to do is to estimate how much the crack is extended each time we unload. And we put that dwell step in because there is a time dependence, and that material is actually relaxing. And if it's relaxing at the same time as you're unloading, then your measurement is affected by that. So the dwell is there to handle the time dependence. So we've done our tests and we've done our calculations, but we also need to validate the results. So most work today on fracture toughness, and yes, there are people researching new and interesting ways to quantify it, but most of the work that's out there being done is based on international standards. And these apply a whole range of validity checks. Why? Well, firstly, we want to operate within the model. We want to operate within the region where the equations are proven to work. We want to avoid experimental effects on the result. And we want to ensure it's comparable with what someone else in another lab does, or with what you did on the last batch of material. So how do we determine these? Well, some of them are based on the test procedure versus the result. So, for example, we're making sure that pre-cracking doesn't affect the crack tip, or the material near the crack tip. The test procedure compared with the static properties of the material. So we're making sure that we haven't got ductility isn't going to be happening outside of the crack region. We're not going to be doing something unpleasant to the outside edges of the specimen. And last, we're looking for specimen. What's our analysis like, and when there are known problems to avoid. For example, if that crack front, like I showed you, is very asymmetric, or, and this is far more common, has a curve to it, that will break the measurement, break the equations, and they won't give you a very good answer. So these are what the validity checks are doing. Toughness test demand today, there are key users, and it is back once again to what I said earlier: aerospace structures and nuclear pressure vessels and the critical structures around power generation, and oil and gas infrastructure. And really that's particularly around pipe work and welded structures. All of these things are where zero critical failures are acceptable. Yes, there are accidents, but well, I say we, the OEMs are bound to design they're legally required to design for zero failures. For example, the overall assessment for the probability of a failure in nuclear power generation is, I believe, the likelihood is supposed to be once in 1,000 years of operation, is the theory. So, very briefly, things have changed in the last maybe 20 years, let's say, in terms of what people expect when they do fracture toughness, or what the market expects. So historically, there would have been some real expertise in the lab operator about how you set up the data collection. Whereas today, we have far more expectation that we can automate that to produce nice, concise data. people would have expected expert assessment of the data. But today, realistically, it's perceived as something far more ironically standard, and the expert in the laboratory would only be supervising and reviewing results, perhaps. The time was that you'd only use highly trained operators to do these sort of critical tests. But realistically, that's, again, driven by how standard and how stable the test methods are. There's an expectation to use less skilled technical operators for many labs. And once again, historically, only really expert labs would have, only a small number of organizations would say they're comfortable and reliable in doing these tests. Whereas today, it's a commodity test data supplied to the OEM, whether you subcontract it or you do it in-house. Then if you're going to supply to someone like Airbus, that batch release data will include K1C measurements. Historically, again, a manual paper trail would probably have been acceptable, whereas in today's world, we really do expect robust digital data systems. And some really interesting conversations I've been having recently with people who run labs, and their auditors, while it's not mandatory, their auditors look for processes which protect method integrity and really ensure that you're working consistently. And, so it always used to look very complicated, and you used to need to know what you were doing. So this is the bit where I'm going to talk a little bit more about the new Instron products which are there to help you. So I'm going to introduce some of the features in our new software package, which we call Bluehill Fracture. And really the idea here is to bring fracture toughness testing up to date, to introduce, rather than lots of windows where you need to know where to go, to introduce a clear, logical workflow, because there is one driven by the standards. To give you explicit analysis and explain and show what's happening if people want to investigate that or check on that. To provide, there's also the need to provide nice integrated tools for reporting or exporting test data. And obviously just making it more helpful. That's something that I think in modern software, certainly we would expect to have help that's helpful, help that's constructive, that gives you advice. And that's there, but also we've built-in features to let you give guidance on screen to your test technicians, if that's what you need to do. And the integration side of things is bringing all of the tests, all the parts of the test together, about pre-cracking and fracture toughness measurement within a single program, rather than doing one stage and then doing another stage. Bringing standards updates in easily and integrating with data management systems within the laboratory. So this is a home screen on when you open the software, and you see it's divided into nice blocks here. I'm actually going to dip out of this very briefly. I have some more slides in the presentation, just in case it was a problem or for when I need to do this offline. But I also have the software running in the background, which I will show you. And as if by magic now, the same screen appears. I'm going to show you first a really, really streamlined test where I've stripped everything out and made it as simple as possible. So I'm going in, I've said I want to do a test, and I pick a method that I prepared earlier. For those of you of a certain age in the UK, then there was a children's TV program called Blue Peter, where they always used to say, and here's one I made earlier. So here's a method I made earlier with it as concise as possible. And I've built in, I've added in the option to import specimen details. So if you've got a lab database, you can create a little specimen file, which is put in a particular place. And we can now pick it up. We can choose, oh, I've got two specimens ready to be tested. So I'm going to pick this one, and everything and all my specimen dimensions will be imported from the lab data management. If I want to, for my traceability, record the serial numbers of my transducers, 1, 2, 3, 4, and 0987, then I can do that. I know that this is a test already because let's say I've got this test method is prepared for a specific thing. I need to confirm what the material form is, and let's say it's cast, and the operator might need to put these things in. We know from tensile test data what the tensile properties are, and we need those for parts of the calculations. Now this is where it's just giving you a summary. I've imported this data that tells me what the width and thickness, what all the dimensions of the specimens are. I'm just going to review it to make sure it does look sane. Yes. And then I can go forward and I'm ready to start my test. And all my test control parameters have all been set and it's ready to go. So that was really very easy to go from opening, I'm going to start a specimen, to getting to start the test. Now I'm actually going to stop that workflow there for a moment and show you the comparison with how many things there are which can be set up, but this operator level doesn't need to see. So I could just say, oh no, I'm not actually going to use that, but I can I've put in all my data and I can save that, and oh, actually I need to stop for the day. I can shut everything down. I can come back later and continue, and you can see down here I've got tests which are part complete. I can pick that one out. That's my specimen ID that I gave it, and I can carry on from where I left off. If I just now, however, pick out a completely empty method, as it were, and say demo web, I need to give this specimen its name. As I now advance, there are lots of extra things, and I can put in lots of different parameters on the specimen geometry. I can define all different aspects of the pre-cracking control. Now, the way I can control that is you can go from this ability to see everything, if you want to equally streamlining it. And I said about streamlining it, we go and we can pick on any of these and prepare them in a method, which will be brought up each time. And but we can also turn on and off different stages. You can see this is really getting into the method creation, which again we can protect, and you can use operator security levels to govern that. And basic operators can't get in here and mess around with the method. They can only edit the things that you've allowed them to. So, for example, I can not show the pre-cracking control settings, and you may have seen as I switched that toggle off, one of my steps disappeared from the sequence across the top here. And similarly, on each of these pages, if I go to the specimen dimensions, I can choose which ones are shown on screen, which ones are important to be measured and entered during the test. So, so a couple of examples there. I'm going to, again, jump out of that. Please excuse the slight background noise there. And look a little bit, I said about showing you the analysis. Let's have a look at an example of a nice K1C test. And here we have, this is a nice, sort of fairly sensible test. And we can see, we can analyze everything. We see some calculated results here, most especially K1C at the top here. And we see the validity checks. Now, if for some reason we've got a questionable specimen, or we are concerned about things, we can look at the validities in detail. We can correlate them with the specimen, with the test standard we're using. We get a description of what it's about, and we can compare what's been measured during the test with what's been what the requirement is. And you can really dig into those details if you want to. Similarly, I can change what my analysis method is. So I'm analyzing here to an old version of E399, and I can step that up to the latest version very easily. And now, unsurprisingly, there haven't actually been any serious changes. Now I've got the latest, reporting to the latest version. But equally, I could use a different standard, and for simplicity, I'm going to use the product test standard here, the ASTM B series standard for aluminium products. And I'm now evaluating, it uses a slightly different set of rules. Equally, I can switch to an ISO standard method. Now here, what the ISO standard requires a few more things. And the reason being, it requires more crack front measurements and some slightly different details in the pre-cracking. So you can see there's all sorts of things here in terms of the detailed analysis that you get and the flexibility to do different things. I'm just looking very briefly. You can also see the ability to customize a report if you want to, giving you either a summary or the full chapter and verse, as it were, of details. Now, I'm alert to the fact that time has got on, and once again, I've talked at great length. So I'm going to skip pretty much to the end. One thing I do want to mention here is about using best practices, because international standards are frequently updated. And if you're going to be an accredited laboratory, you need to demonstrate you're really on top of compliance with the latest version. Yes, the changes aren't always very much, but it can be a real stumbling block for some laboratories. And the other thing I'd say is that the standardization in terms of how you do the analysis is increasingly prescriptive. And it moves you away from expert assessment to very carefully specified algorithms, and doing more and more computer-based number crunching, as it were. So really doing those best practices is becoming more and more programming intensive if you're going to do your own analysis. And it's something that some of our customers see as a real benefit to working with us on fully compliant methods. So wrapping up, I'm sure people have got lots of questions, but in summary, we've got, as I said, we're looking at the resistance to local failure near a defect in material. And this is something that's essential to engineering design for critical structures. There are a range of different ways of measuring it, both in terms of the mechanical test and in terms of the parameter that you use. But I hope you've got this, my very brief tour there of a few features in our new software helps you see that the market is changing, and we have worked really hard to bring modern software that's evolved with it. So I gather that there's been a lot of interest in this, in joining this webinar in advance. Hopefully people who've been with us have found it interesting and at least a little bit informative. I think this is something that we're going to do more presentations on in future. So if you are interested in then look out. I'm going to say thank you very much for your attention, or at least I hope there was some. And my colleague Lisa Goodwin has been looking out for questions and is going to relay a few of them in the few minutes we've got left.
Thanks, Pete. A few questions coming in, some asking about control modes that we use for running these tests. So I don't know if we can quickly run through that. I was explaining that depending on whether you're doing fracture tests for crack growth or fracture toughness, then the control modes are different.
Yes, so in pre-cracking or crack growth, then you fundamentally, your machine is being controlled on the force signal, but you're adjusting that so that you can either do constant force or you can modulate that force so that you get a gradually increasing or a decreasing or indeed a constant stress intensity. Because as the crack grows, you need a different force for the same stress intensity. When you look over at fracture toughness, then typically the most common way is to go at constant displacement rate. So you're in position control of your machine and you're driving your actuator or your crosshead at a constant rate of movement. Those are the main things that we see people asking for. Occasionally people choose to control from the extensometer, which is great, but it is far higher risk because if you have a sudden specimen failure, it will fall off, and you're then relying on the higher level control of the system to protect it. I hope that's helpful.
Okay, how do we decide if we should be running a J or a K test? So that's relating to either the brittle or the ductile type failure tests.
Yes, so there's a sense of that. I think if you are coming to this, I've put an extra slide in behind this because it's something that can come up. I've borrowed a picture here from a textbook about how you get clues from a tensile test. It's really your tensile test, both the physical appearance and the plot from it will give you a very strong clue. So if you're looking at something ductile, very ductile, you get a lot of stretch and you get this what's called cup and cone shape on the tensile test. And when you look at your force displacement or your stress strain plot in tension, you'll get an initial linear slope and then a gradual curve across and quite a lot of strain before failure. By contrast, if you look at the brittle fracture, it's usually there's very little necking, very little reduction in cross-sectional area, and typically a very flat fracture surface or breakage across the specimen. And your stress strain plot will go up in a nice straight line and maybe curve over a little bit, but then a very abrupt failure. So if you're seeing that really ductile behavior in tensile, then I would immediately start looking at a J1C type test. But if you've got something brittle, then certainly attempt a K1C test. It is far simpler in both analysis and in test preparation. I hope that helps and that's fairly clear. I mean, we're at the time limit here. Any other questions that look fairly quick to you, Lisa? If not, then obviously we will we'll follow up with people if we haven't had time for your question during this session. I'm hearing a resounding silence out there, Lisa. Harriet, can you hear me still?
Not to worry, Pete. I think, are you all right, Lisa?
Yeah, a lot of the questions are pretty long. Sorry, I'm trying to read at the same time as.
Oh, no, that's fine. I
talk to you.
wasn't sure if we'd lost you there. It all went quiet. I'm sure that some people may need to be leaving if they and that. So I'll say thank you very much for joining us if you are having to. Just trying to see what's going on. So were there any that leapt out for you as you there, Lisa?
Sorry, Pete, nothing quick. Nothing quick.
Okay. Well, in that case, sure. What we'll do then, like I say, I think we will be talking more about this in forthcoming months, and so we might be covering some of that. What we'll do then is, given the time, we will look through your questions and try and get in touch with you. Either if it's fairly straightforward stuff, either your local team will drop you an email, or some of the more complex questions, maybe I'll pick up and you'll get an email from me over the forthcoming days. So I'm sorry I spoke for too long and there wasn't much time for questions. So once again, I'm going to say thank you very much. Have a great remainder of your day, and I shall sign off for now.
Thank you so much, Peter and Lisa. Just a quick note before we do wrap up. The recording from this session will be available on our YouTube channel in just a short while, and each of you will also receive an email with a link to the recording. I just want to thank Peter again for a great presentation, and thank you, Lisa, for your help with the questions. And thank you to all of you for attending. We really appreciate your time.